Hello to all the ISBI 2020 community and welcome to the presentation of our paper Unsupervised Task Design to Meta-Train Medical Image Classifiers, developed by Gabriel, Maicas, Nguyen, Farbod, Motlagh, Jacinto, Nascimento, and Gustavo Carneiro at the University of Adelaide and Instituto Superior Técnico. The training of medical image classifiers based on deep learning relies on large datasets. However, in medical image analysis, it is not often possible to collect and annotate such large datasets. To reduce the need of annotated data, several strategies have been proposed. For example, we can pre-train the model using techniques such as supervised pre-training using an independent dataset, unsupervised pre-training using clustering, where the model is trained to cluster the training data, or unsupervised pre-training using reconstruction, where the model has to reconstruct the training images. The main issue related to these methods is that the training objectives are irrelevant for the downstream task. Other training methods that have been shown to work relatively well with smaller datasets are multiple instance learning or multitask training. But recently introduced, supervised meta-training has been shown to be the most effective of these methods. However, it relies on a costly hand-designed process to produce the classification tasks. In our work, we aim to reduce the cost of manually designing tasks by unsupervisedly producing the large number of classification tasks required to meta-train a medical image classifier. So how does the supervised meta-training strategy work? In the first step, using the training set, we manually build different tasks or classification problems. We then meta-train the model, which means that we ask the model to solve each of the meta-training tasks. Once the meta-training step has converged, we then fine-tune the meta-trained model in the task we are interested in. Finally, we can run inference as that of any other model. This supervised meta-training process has achieved state-of-the-art results. However, it relies on an expensive hand-designed process to produce the classification tasks, which is not scalable for medical image analysis, given the high number of hand-designed classification tasks required. In this paper, we propose to eliminate the burden of handcrafting tasks for the meta-training step, and therefore build the tasks automatically. To automatically build meta-training tasks, we use deep clustering to cluster the training data into different clusters. We then build the tasks by forming all possible binary classification problems by randomly selecting two subsets of the cluster. These tasks are then used to meta-train the model as explained in the previous slide. After convergence, we fine-tune the model in the target task. Finally, we can run the inference as that of any other model. As with supervised meta-training, unsupervised meta-training consists also of a meta-training and a fine-tuning stage. The only difference is how the tasks are built. While supervised meta-training relies on the costly procedure of hand-designing tasks, unsupervised meta-training uses automatically built tasks. We evaluate our proposed method on a breast DCE MRI dataset, which has been previously used to evaluate few-shot training methods. 45 patients are used for training and meta-training, and 59 patients for testing. We are particularly interested in the breast screening problem, where a breast is considered positive if there is at least one malignant tumor or negative otherwise. Note that our methodology runs breastwise. To compare the performance of our model with other baselines, we use the area under the ROC curve or AUC in the breast screening tasks. The underlying model that is meta-trained and fine-tuned is a denser, but please see the paper for more experimental details, including details about the training process. In this table, we compare our model against other training methods. We see that our proposed unsupervised meta-training strategy achieves an AUC of 0.89, outperforming the rest of the baselines. Our model also improves the traditional training from scratch strategy that only achieves an AUC of 0.83. And also, it improves other pre-training strategies that are introduced at the beginning and are based on using another dataset or based on clustering or reconstruction. Note that our method also improves the results of other training strategies focused on a small training sets, such as multiple instance learning and multitask training. How does our model compare to supervised meta-training? We present the results in this table, where we see two different ways of sampling tasks. Randomly are based on curriculum learning. In curriculum learning, tasks where the model does not have a constant performance are sampled more frequently. In the table, we also see the parameter K that determines the number of clusters that are used to build the tasks. We see that our proposed unsupervised meta-training method with an AUC of 0.89 produces results comparable to the state-of-the-art set by supervised meta-training that has an AUC of 0.9. With the advantage that instead of using manually defined tasks during meta-training, we unsupervisedly build classification tasks, which also allows us to build a larger number of tasks. Also, we can see that a larger number of tasks, which increases with the number of clusters, generally means a better performance. Note that this fact is different to computer vision, where a high number of manually designed tasks are already available for unsupervised meta-training. And then having more tasks to meta-train does not imply a better performance. But for further reading about this topic, we encourage you to read our paper. Here we can see qualitative examples of diagnosis produced by the model trained with the proposed approach. In the top left, the model correctly diagnoses a breast with a malignant tumor. In the top and bottom right, we can see two true negatives. In the top right, because there is a benign tumor, which is considered negative in the breast screening task, and in the bottom right, because of the absence of any tumors. In the bottom left, we can see a false positive diagnosis of a breast with no tumors. To sum up, I have presented a new method that unsupervisedly designs classification tasks to meta-train medical image classifiers, where the main goal is to reduce the burden of handcrafting a large number of classification tasks. Results show that our proposed method outperforms several baselines consisting of traditional pre-training methods, multiple instance learning and multitask training. Finally, our method also produces results comparable to the state-of-the-art set by supervised meta-training that uses hand-designed classification tasks. Here's a list of the main references, but please check our paper for a full list of references. Thank you very much for listening, and please contact us if you have any questions.